Every time I watch a Marvel movie, there's this one thing that always gets me. It's not the aliens, it's not the magic. It's Captain America's shield.
Oh, yeah. Or the Black Panther suit.
Exactly. They just say vibranium, and suddenly you have this magic metal. It absorbs everything. It never breaks. It basically just ignores every law of physics we learned in high school.
It's the ultimate plot device, like Mithril in Lord of the Rings.
Light as a feather.
Hard as dragon scales.
Right.
It's a perfect material because it solves every problem.
But in the real world, metallurgy is always about compromises, right? It's a series of disappointments.
Huge trade-offs, always.
You want something hard, it's going to shatter. If you want something that bends without breaking, it's probably soft and heavy. We don't get vibranium. We get, like, cast iron pans that crack if you look at them wrong.
Or aluminum cans that dent if you sneeze. And that has been the reality for, 5,000 years? The golden rule has always been that trade-off. Strength for ductility, heat resistance for brittleness. You just can't have it all.
Well, welcome to the Deep Dive Lab, because today we're looking at a huge stack of research that suggests we might finally be cheating that system. We've gone through this massive literature survey, talking over 15,000 studies, papers from Nature, Science, and it all points to a concept that sounds, well, frankly, more like sci-fi than blacksmithing. High-entropy alloys.
It is genuinely a paradigm shift, and I don't use that phrase lightly. We are, in effect, moving from the Iron Age or the Silicon Age into what some are calling the Entropy Age.
The Entropy Age.
Right.
I mean, that sounds a little ominous. But before we get to the starship parts, I want to ground this. You had a great analogy for how we used to make alloys, the Batman and Robin method.
Right. So if you look at pretty much any alloy we've ever used, it's based on one main element. Steel is mostly iron.
Okay.
Brass is mostly copper. Aluminum alloys are, well, mostly aluminum. That principal element, that's your Batman. It does 90% of the work.
And all the other stuff, the carbon in steel or whatever.
Those are just sidekicks. The Robins. You sprinkle in tiny amounts to tweak the properties a little bit, make it harder, more rust resistant. But they are guests in Batman's house.
But this new approach, which really kicked off with a paper by J.W. and his colleagues back in 2004, it just flips that whole idea on its head.
Completely.
They basically said, forget the sidekicks. What if we just make a team of Batmans?
Exactly. An ensemble cast, let's mix 5 or more elements in basically equal amounts. So, 20% cobalt, 20% iron, 20% nickel. No single hero. It's the Avengers of metallurgy.
Okay, but see, this is where my brain starts to hurt.
Yeah.
If I go to a soda fountain and I mix every single flavor, I don't get a super drink. I get that suicide soda that just tastes awful.
Right.
Shouldn't dumping 5 random metals together just create a brittle, confused mess?
Your intuition is spot on. Traditional metallurgy says, yes, absolutely. The atoms should try to separate into these little clumps, these intermetallic compounds, which are usually totally useless. It should be a disaster.
Like a first-year potions class in Harry Potter just went boom.
Precisely. But what Ye's team found was that it didn't. It formed this simple, incredibly stable crystal structure. And that is where we have to talk about entropy.
Right, high-entropy alloys, HEAs. Now, when I hear entropy, I think second law of thermodynamics.
Yep.
Chaos, disorder, my apartment after a dinner party. So why does adding more chaos make a metal more stable? That just feels backwards.
It does feel counterintuitive, but it comes down to gives free energy. I promise, no math. The concept is that nature always wants to be in the lowest possible energy state.
Okay, low energy equals stable.
Got it. Right. And there are 2 forces fighting over that state. One is enthalpy. That's the desire for atoms to bond in neat, orderly ways. The other is entropy, the desire for randomness.
So enthalpy is the neatly organized file cabinet, and entropy just wants to dump all the papers on the floor.
Perfect analogy. Now here's the twist. The equation multiplies entropy's effect by temperature. So at very high temperatures, like when you're melting all these metals, entropy gets a massive power boost.
So because you have 5 different metals all jumbled up, the randomness factor is so high that it just overpowers the need for order.
That's it. The system looks at its options and sees that staying in this simple, chaotic soup is actually the lower energy state. We call it the cocktail effect. The atoms are basically trapped in the chaos because it's just too comfortable to leave.
The chaos is the glue. That's wild.
Yeah.
But does it actually matter? Does this cocktail effect give us better metals, or is it just a cool parlor trick for physicists?
So it's definitely not a parlor trick. This is where we start breaking those rules we talked about. Let's start with the big one, the strength ductility paradox.
Yeah, this is the classic trade-off. Hard things snap, flexible things are weak.
Correct. But if you look at a study from Nature and PNAS on an alloy called NiUroFev, Well, it breaks the curd.
I was looking at the charts for this. It claims a yield strength over 1 gigapascal. For anyone listening, that's like high-grade titanium territory.
It's super strong.
But then it says it has 30% ductility, which is just absurd. It sounds fake. That means you can stretch it by a third of its length before it breaks. At that strength, ductility should be near zero. It should shatter like glass.
Yeah.
How is it cheating?
It's using something called hierarchical ordering, because all the atoms are different sizes: nickel, cobalt, iron. The crystal lattice is all distorted and bumpy, so when you apply stress, it doesn't just break. It has this whole sequence of defense mechanisms.
Like what?
First it slips, then it twists, then it forms these tiny internal barriers. It's like having a suit of armor that's as hard as diamond, but it moves like spandex because it has 5 different ways to absorb the hit at the atomic level.
Okay, strong and stretchy. What about toughness in extreme environments? I keep thinking that scene in Terminator 2.
The liquid nitrogen.
Yeah, the T-1000 freezes and
That
then...
shatters into a million pieces. Yep. That's what cold does to most metals. It makes them incredibly brittle. But there's this study from Lawrence Berkeley National Lab about a medium entropy alloy, GR Coney.
Just 3 elements: chromium, cobalt, nickel.
And this might be the most shocking finding in the whole field. They cooled this alloy down to 20 Kelvin, that is minus 423 degrees Fahrenheit.
Deep space temperatures.
And instead of becoming brittle,
It got tougher.
way tougher, it set a record for one of the highest toughness values ever measured for any material.
How? That makes no sense. How does freezing something make it harder to break?
It's a mechanism called nanot winning, and it's so cool. When you put the alloy under stress at that low temperature, the atoms spontaneously rearrange themselves into these tiny mirror image patterns.
Mirror image patterns, like on the inside.
Yeah. Imagine a crack trying to spread through the metal. It's moving along, and then bam! It hits one of these twin boundaries, which is like a microscopic wall, and it just stops dead in its tracks.
So the stress itself triggers the metal to reinforce itself.
The pressure causes it to build its own internal armor, second by second. The material is essentially healing itself by blocking fractures while it's being attacked.
That has an immune system. Okay, that is amazing. So we've done Hoth. What about Mordor? You know, inside a jet engine.
Heat, the other great enemy. Our best jet engines use nickel superalloys, but they're at their limit. If we want more efficient engines, we have to burn fuel hotter.
That's just basic thermodynamics, right? The bigger the temperature difference, the more work you get out.
Precisely. Every single degree matters. But with these refractory high-entropy alloys, using things like niobium, tantalum, we're seeing a whole new ballgame.
I saw a report that said these can operate at over 1,500 degrees Celsius.
Hotter than most lava. If we can build turbine blades out of that, we can stop worrying so much about cooling them. We can strip out weight, complexity, the engines run hotter, planes fly farther on less fuel. The impact would be massive.
Okay, so we've got a material that's super strong, flexible, invincible in the cold, and doesn't melt in a volcano. It feels like we solved everything. But there's got to be a catch.
There's a huge catch.
Because if I'm an engineer, I'm looking at a recipe with, say, tungsten and aluminum, and I'm thinking, how do I even mix these? Tungsten melts at over 3,000 degrees. Aluminum boils at 2,500.
You've hit on the manufacturing bottleneck. If you use a standard furnace, the aluminum is just a puff of smoke before the tungsten even gets warm. You can't just stir it with a spoon.
So how do you cook the chaos recipe?
You use speed, extreme speed. The game changer is 3D printing, specifically something called laser powder bed fusion.
Sounds like something from Star Trek.
It really feels like it. You lay down a super thin layer of metal powder with all 5 elements mixed in. Then a high-power laser zaps it, melting it instantly. But here's the key part. It cools down at a rate of 1 million degrees per second.
1 million.
Per second. It's basically instantaneous freezing. You trap the atoms in that chaotic high-entropy state before they even have time to realize they shouldn't be together. You freeze the chaos in place.
So we're 3D printing objects that shouldn't exist by flash freezing them into reality.
Exactly. And we're getting even faster. A study in Nature talked about thermal shock synthesis. They're heating materials for just milliseconds.
Milliseconds. Why?
To trap volatile elements like zinc into a lattice with things like iron. Usually, the zinc would just boil off and disappear, but they shock it so fast it gets stuck. They're using it to make these amazing nanoparticles for clean energy.
This brings up a new problem, though. A paradox of choice. If the rule is just mix any 5 elements, and we've got, what, 70 useful metals on the periodic table?
The math gets scary very, very quickly.
I tried to calculate it. Just picking 5 from 70 is about 12 million combinations. But if you start changing the percentages, 10% of this, 30% of that, the number of recipes is.
It's bigger than the number of atoms in the universe. It's a combinatorial explosion. You could never test them all by hand.
So we have an infinite kitchen with no cookbook.
Which is why the entropy age is totally tied to the AI age. We're using machine learning and a method called CLPHAD.
This is the Dr. Strange part, looking at 14 million possible futures to find the one that works.
It really is. Researchers train an AI on hundreds of thousands of alloy compositions. The AI learns the deep physics, atomic size, electrons, all of it, and it predicts which recipes will work.
So instead of mixing metals in a furnace, we mix them in a computer first.
And it has over 90% accuracy. They use this exact loop to discover a whole new class of INVAR HEAs.
INVAR, as in invariable.
Yes. Metals that do not expand when you heat them. Normally, heat makes things expand, a total nightmare for precision instruments. But the AI found a recipe where the magnetic properties of the atoms fight back against the vibration. The metal stays the exact same size, hot or cold.
That is just mind-boggling.
Yeah.
We're not just discovering materials anymore. We are programming them. We are telling matter how to behave from the atom up.
We are turning the periodic table into a box of Legos. We can just design the properties we want, ask an AI for the recipe, and print the part with a laser.
It's so exciting, but it's a lot to take in. Let's bring it back down to earth for a second. If you're going to remember just 3 things from this deep dive into chaos, what should they be?
Okay. Takeaway number 1 is the shift. We've moved from the solo hero model of alloys, iron plus a sidekick, to the ensemble cast of high-entropy alloys. 5 or more elements held together by chaos itself.
Takeaway number 2, the superpowers.
Yeah.
These things cheat the rules. They're strong and flexible. They get tougher in the cold because of that nanot-winning thing,
Yeah.
and they can survive inside a volcano.
And takeaway number 3, the method. The kitchen is just too big to explore by hand. We're using AI to write the cookbook and 3D printing to flash freeze the recipes into reality.
It really does feel like we're on the edge of a new era. You called it the entropy age.
I think that's what history will call it. This is a fundamental change in how we build our world.
So as we wrap up, I want to leave you, the listener, with one last thought. We've talked about all this amazing tech, jet engines that don't melt, phone screens that never crack. But zoom out.
The economic implications.
Exactly. I mean, our entire modern economy is built on things breaking, planned obsolescence. Cars rust, parts wear out, you buy a new one. That's what drives consumption.
A permanent product is a business's worst nightmare.
So here's the question. If we can print a car engine that runs for 100 years without wearing down, or build a bridge that never needs repairs, what happens to our economy? Are we ready for a world where things simply don't break?
That is a question that might need a deep dive all on its own.
It sure is. Thank you for hanging out with us in the Deep Dive Lab. We hope your brain is feeling a little more high entropy than when you started. If you enjoyed this journey, hit that subscribe button. We've got plenty more mind-bending topics coming up.
Stay curious, everyone. See you next time.